Today we are going to continue on what we have learned about carrier actions in semiconductors. Basically we learned about generation of electron and holes, recombination, their response to the electric field, drift motion and the diffusion motion. And now it is time to see how all these things take place in a semiconductor material or a device, which then finally gives rise to a device characteristics. So, to summarize, in previous lectures what we have learnt about carrier action is RG processes, recombination generation processes, in which we learned that from conduction band and valence band we can generate carriers and we can, in this process we generate, that is generation of carriers, and when these recombine, this is recombination process. We learned different mechanisms which make the RG processes possible, and we also learned how to take into account change in the carrier concentration due to these processes. We also learned about drift, which was response of the carriers to electric field, which basically means if there was a field applied in this direction, this would mean that electrons are going to move opposite to the field in the conduction band, and the notional holes that we talk about are going to move in the direction of the field. Hence, we can write about the current as due to electrons in the conduction band plus the current density rather than current, and holes in the valence band. Similarly, we also learned that if you do not have uniform carrier concentration in the device, then we will also have a diffusion process, which would also lead to current due to diffusion, and again this will be due to electrons and due to holes. So far we learned about these processes as individual processes, but when we talk about a device, all of them are occurring simultaneously in the material. So, all these processes occur simultaneously in semiconductor materials, in semiconductors in a device, and hence we need to find a way of dealing with them at the same time what is happening in the material. So, if we consider all of them together, what we can talk about is, let us say if I have a semiconductor, and so far I am not trying to bring in the device, but if I have a semiconducting material and at any particular point, and let me think only about one dimension right now, I want to figure out how is the concentration of electron changing with time here, or I could also say that how the concentration of holes is changing with time here, but let me just talk about electrons right now. Then I can say that change in this particular segment of a material, change with time is going to be a resultant of all the processes that we have talked about, which means how many of the electrons due to some if there is a field here are going to go out, or how many will come in. It would be a result of how many due to drift. It would also be a result of how many are going to change due to diffusion minus how many will come in. Net value of this will give me a change in the electron concentration here. So, I can write that those two processes in terms of d and dt drift due to drift process due to response of the field, assuming there is a field here at the moment, plus, so we are writing a general equation, change in the electron concentration due to diffusion, net electron concentration in this segment due to diffusion. Plus, at the same time we know that we can have processes here, the RG processes, which would lead to generation or net annihilation of the carriers. So, that would be additional term which would lead to change in the concentration it is a term like source or sink for mass or heat continuity equation. It is a similar term for electron carriers in this context. So, this we would write for RG processes, and generally when we talk about RG processes, this is also what we are talking about, which are mainly thermal processes. And then we split out another term for generation, which may be due to external sources, which is change in the carrier concentration due to other processes. What are these other processes? As we discussed, the generation can be due to thermal reasons, or the generation can be due to the injection of carriers or due to excitation by a light source. So, this would be a general equation which is basically having 4 terms: drift, diffusion, RG processes, which are thermal processes leading to change in carrier concentration at that point, or other processes. We have plotted it in this manner, but you can think of it, this is in general it will be a concentration of carriers will be a function of its position in the material and time, and hence the equation is going to be in general terms. So, now if we look at it and try to figure out what this equation means, let me look at it in terms of overall continuity. This equation is basically a continuity equation, very similar to what we have in mass and heat continuity equation. It is continuity equation for carriers and semiconductors. It is providing information about continuity of what is happening at a given point in the semiconductor and in time also. Continuity of carriers in space and time. So, this general equation that we wrote earlier tells how the carrier concentration at a particular point is related to the carrier concentration to its adjacent point and how it is changing with time. So, that is a general equation. If we try to make it a little bit more simplified, then we know that change in the concentration, if we take the first term due to drift and diffusion, we know that the change in carrier concentration can also be written as if there is going to, this is going to be the gradient of the electric current due to electrons. Similarly, one could write the counterpart for holes when the whole equation has to be written, where this would be given by negative charge, and you know the source for the negative charge is because conventionally the current is taken as the flow of the positive charge, and for flow of the negative charge it is the direction is negative to the flow of the negative charge. So, if we write the change in concentration in a general term, then this can be further specified. What is J n? J n here is overall J n due to drift plus J n due to diffusion, and you can write equivalent terms here for holes. Similarly, the second term, which is the change in the concentration due to RG processes, we make a short form of it and write it as negative of, as if this is basically recombination of carriers or loss of carriers. So, we give it a symbol R n, and for the fourth term, which is a change in carrier concentration due to other processes, for most of the discussion in this course, we will limit it to only photo generation, which is given a symbol here as J L n. So, this is we limit other sources to only photo generation. So, if we take these short forms for the continuity equation, then what we will find is that the continuity equation can be written in short by del n del t is equal to 1 over q gradient of the current due to electrons plus the generation if it is confined to the photo generation only. The counterpart of it for holes will be written, continuity equation will be written as del P del T will be negative of 1 over q gradient of the current density due to holes minus a thermal RG process term plus G P. So, this is my general form for continuity equation. This is the general form for continuity equation. Which is a simplified form for optoelectronic devices. Now, this is the starting point for analyzing the devices. If I need to know in a device what is the behavior, I would need to solve these equations and try to figure out what is the change in x, y concentration of carriers as a function of where it is and as a function of time. And so, this is basically the beginning of the analysis of the device, where we will take the all the carrier actions in the semiconductor into account and figure out what would be the device characteristics. And by using this equation, I can solve for n x y z or p x at any position in the device as and also as a function of time. Now, these are not in themselves sufficient, because we need additional information. So, let us try to see what all we know, the equations that we need to solve in order to find a solution in a device. So, if we summarize all the equations that we need to solve, then we know initially we learned in addition to these equation, we need to solve that the charge density at any point in a semiconductor will be given by the number of electrons plus will be given by the number of holes minus the number of electrons plus the number of donors ionized positively minus the number of acceptors ionized negatively. This would be given by charge density. If we know the charge density in the semiconductors, the next equation that we need to know is the Poisson's equation that solves for, which is a differential form of the Gauss's equation, which looks for the gradient of the field is given by charge divided by the dielectric constant, where dielectric constant in a material is relative dielectric constant and the electric permittivity of the vacuum. In addition to that, we have learnt during drift that current due to electrons is current due to electrons due to drift. But prior to that, let me make a general statement. The total current density would be current density due to electrons and due to hole, as if electrons are moving independently and holes are moving independently in the conduction and valence band respectively. And the current density of electron is going to be given by the drift term, which accounts for the mobility of the electron and the electric field, plus the diffusion terms, which accounts for diffusion coefficient and the gradient of the electrons. Similarly, the current density due to the holes will be given by the drift term minus the diffusion term for the holes. So, this we learned during our discussion in the drift lecture. This we have learned earlier in module 2. And then finally, we have come up with the continuity equation here. So, these equations together, when one solves these equations together, one finds a solution of steady state or dynamic behavior of the device. So, that is this is why we say this is the starting point of device analysis. Any device analysis starts from these equations, and they are you can see interdependent on each other, hence they all have to be solved simultaneously in order to find a solution. And this is what the starting point of many device simulator is, which are existing commercially also, but one needs to know this basic knowledge in order to use them and find a solution to various device characteristics. Now, we would like to simplify this problem and talk about a simple solution here, because computer simulations are not possible over here. So, we will look at a special case of this continuity equation, and which is very common in many devices, and which we will also use later in the course, and that is for the situation when we have devices where we have the state of low level injection. What does low level injection mean? We have earlier come up across this term when we were talking about generation of carriers. It basically means if I am generating electrons or if I am generating holes, their concentration is much less than the majority carrier concentration and not, if this is a n type device, n type semiconductor, or if it is a p type semiconductor, then the excess carriers generated is always much less than the majority carrier if it is a p type semiconductor. So, for many devices this situation is true. So, we find a simpler form of the continuity equation that we will solve easily and use certain assumptions. So, we will make some assumptions to find another form of the continuity equation, which is basically used for minority carriers. Under low injection level, basically we can say that number of in this situation the number of minority carriers generated are going to be important, because number of majority carriers generated are so much smaller to the majority carrier concentration that it is not going to make a huge difference, but the number of minority carriers would make a huge difference. So, we are analysis is getting limited to the minority carrier equation, and in the simplified form from general continuity equation we are going to make certain assumptions for this equation. First of that is, again we will assume a one dimensional system, which basically says that all our carrier concentrations are changing only in x dimension. So, all changes are in x dimension, in x direction, and other directions things are relatively constant. We also make the assumption that we are only looking at minority carriers here, and we are looking at a situation where electric field generated is 0. So, there is no electric field in this particular simplification, and we also make an assumption that the at equilibrium n is not a function, the equilibrium concentration is not a function of x, or for p type it is not a function of x again, which means it is a uniform doping. Further assumption we make, it is a low level injection, which I have already mentioned. So, for low level injection we are going to solve this equation or simplify the continuity equation. So, it is low level injection situation, and we will apply these conditions to see what will happen to the continuity equation. So, if we continue that discussion, again let us write the general form of the continuity equation here, which is which we have simplified to and let us look at all the terms on what is happening in each of these terms, and if we follow that, then let us look at the first term here on the right hand side. So, 1 over q gradient of the electric the current density due to electrons is going to be 1 over q, and since the problem has been simplified to one dimension, I can only worry about del over del x and expand j of n. This is going to be mu of n electric field plus q diffusion coefficient for electrons times del n del x. Now, immediately you can see, since we have said that there is no electric field, this term is going to go to 0. So, we are going to simplify this as and q of d n will come out, which would give us q of d n. So, finally, term will be d n gradient of x square. If you look at the term r of n, we have done in the recombination generation under the low level injection. The recombination rate for a low level injection can be written as del n of tau over n, where tau of n is basically minority carrier lifetime. Lifetime of the material. And simplifying this to this situation, then we can write the left hand side of this equation. Del n del t is nothing but equilibrium concentration plus the excess concentration divided by del t, and since we have equilibrium concentration is not changing with time, this would be simplified to the excess carrier concentration to del t. Similarly, I can write make this similar analysis for the second and the third term. Then I would write the overall continuity equation for minority carrier continuity equation will be del n, rather than writing for the total carrier concentration, we write a equation for excess carrier concentration, which is going to be given by d n, second derivative of the concentration gradient plus g of. So, I have changed and similarly I can write for this as well for the excess carrier concentration. So, what we have done here is we have changed the continuity equation from equation which is written in terms of the carrier concentration or electron concentration to excess electron concentration, and which basically means then we are solving for what is happening to the excess electron concentration in a device. A counterpart of this can be written for holes also, which would mean this is going to be for minority carriers. This equation will be written as dP for excess hole concentration given by so these two equations are for minority carrier continuity equation, which would be solved for many situations. Let us take some examples. So, we will take the first example and apply it to get some solution. So, the first examples here are the first one is, let us say if I apply look for a steady state solution. If I am looking for a steady state solution, what will happen to the minority equation, and concentrating on the first one, which means the first term here is 0. So, for a steady solution this will become 0, and the second term will remain, and that will be d of n, second order differential, second derivative for delta n minus delta n p over tau n, and this the solution for this can be obtained. There is a possible solution, and this you can look up in any solution book. What are the typical solution for such a equation, and assuming here the photo generation is 0, GL is 0, then typical solution for the axis carrier concentration in P will be of the type which is given by ln plus C2 exponential minus x over plus x over ln, and then this is the constants which need to be evaluated for a given boundary condition. Then there are certain other approximation that we encounter often in the device physics, and the second one is when there is no concentration gradient. So, when there is no concentration gradient, what will happen to the minority diffusion equation? In the no concentration gradient, the term this term will become 0, and you are left with the transient of the axis as a function of time. This one becomes 0 is equal to and a solution for this type of differential equation is typically basically delta n of p at a given time t, given by what is the carrier concentration at time 0, and it is reducing with the time constant of the lifetime of that carrier, which is in the p type material. So, you can see how we from a general equation we can get some very simple closed solution for under certain approximation. The next one is the next approximation or example is when we have a problem which is in a steady state, and there is no concentration gradient, and in addition there is no generation of photocarriers, this is also 0. If I am looking at this situation, then what happens to the the solution? I am left with basically del the left hand side is equal to this is actually already steady state. So, this is also going to 0, there is no concentration gradient, hence the second term which is the second derivative is also going to 0. I am only left with the third term, and I have already said that the no, this is wrong, sorry, this the photo generation is there. So, this would be under the condition where there is photo generation, and if I look at now this equation, the solution for this is simply the change in the carrier concentration is given by the amount of photo generation multiplied by the lifetime. So, this is the axis carrier I generate. This is a very simple problem which has a very simple physical interpretation. What am I saying? I am saying here I take a semiconductor in which I am looking at the change in the carrier concentration. Thus, say this is a p type semiconductor. I am looking at the carrier concentration of electrons in the p type material, and I am shining light on it. I am shining light, and it is creating certain electron and hole pairs at some rate per second, and I continue to shine. Eventually, the electron and hole concentration in the semiconductor will increase, that will increase the recombination rate for those carriers, and then it would eventually lead to a steady state. Hence, I say it is a steady state solution. The first term goes to 0, and then I say I take a material for which I am shining light sort of uniformly everywhere. So, it is not that there is more carrier concentration here compared to here. So, if I am shining light uniformly, the second term also goes to 0, then I am only left with the third and fourth term, which has a simple solution that the axis carrier, the axis steady state carrier that I am generating is equal to the rate at which I am creating the axis carrier multiplied by the lifetime of the electrons or the minority carrier in that material. So, this is a problem which we will encounter again when we come to the next module, and we have a solar cell and we are trying to see how many carriers are generated there. Let us look at one more example, special case for the minority diffusion equation, and this one is when you are looking at in a steady state where there is no RG thermal process and also there is no light, which means the first term, the third and fourth are 0. I am only left with the equation which is the second derivative of the axis carrier concentration. Now, the solution for such a equation is very simple. It is basically the axis carrier concentration in x will be given by some constant times x plus b. So, we have looked at 4 different situations in which I can apply the minority diffusion carrier equation and find a closed solution, which is also physically meaningful, and we looked at one case of generating how many axis carriers are generated in a steady state when I shine light on a semiconductor. So, at this point let me summarize all the equations that we have learned so far. So far we look at all the processes that are happening in the semiconductor, and we say, well, we cannot destroy or create carriers, and hence you must have a continuity equation, and writing it for both the type of carriers, because in semiconductors the overall current is addition of current due to electrons and holes. So, I will write continuity equation for the for both the type of carriers. So, the change in this is going to be given by, in its short form, 1 by q gradient of the current due to electrons plus del n del t due to RG thermal plus del n del t due to other processes. Similarly, I will write for holes, because they both work independently, they have to be solved independently, both equations. I will solve for hole concentration, which is RG thermal plus del n del t, del p divided other processes. Now, this is the general form of the equation, and then we reduced it to some simple approximations and gave the equations for minority diffusion, under the approximation for minority carrier diffusion equation. And in that approximation we showed that these two equations will reduce to basically the axis carrier concentration being given by the second derivative of the axis carrier concentration by the lifetime of the minority carrier plus the photo generation. And similarly, I would solve it for holes also, and this will be given by, for the diffusion of holes, the second derivative of x is hole concentration in n type material minus the recombination due to thermal processes and the photo generation. Now, in addition to these equations, we also need to solve another equation which we have not discussed so far, and that is, if I look at this particular expression, the general equation, I am solving for the n and the p in the first equation, and then I look for the current due to electrons and holes. But remember, the current due to electron and holes is dependent on the electric field, and electric field itself is changed when there is a change in the density of charged particles in the material. Hence, it is one uses the value of electric field in this equation, which itself depends on the value of n. So, you are solving something which depends on itself. So, it is kind of a iterative solution one needs to look for, and in order to do that, we need to calculate for every solution that we find, we need to calculate what is the change in the electric field. And so, how do we calculate the electric field? And for that we use another equation which we have not discussed with the equation of state, but it is needed to solve the continuity equation, and that is known as the Poisson's equation, which relates the electric field in the semiconductor, the gradient of the electric field is given by the charge density divided by the dielectric constant of the semiconductor. What is the charge density? Now, keep in mind, this is not resistivity, although the symbol is same, this is not resistivity, this is the charge, it is charge density. And in a semiconductor, then rho is equal to the rho is equal to the charge on the holes minus the charge on the electrons, and the number of the holes minus the number of electrons plus number of donors, ionized donors, minus the number of ionized acceptors. So, this is a charge in the semiconductor which we need to feed in this equation to calculate E, and then this electric field is used in this continuity equation to get the value of n, and once again, once you get the value of n, you have to again calculate E, and finally the solution will converge to a value, and that would be your final solution. So, we use the Poisson equation in order to solve this. The other supplementary equations that I used here and that we have been discussing earlier, the current due to the electrons is given by nothing but q times due to drift electric field plus due to the diffusion of the carriers, the gradient for n. I can write the same thing for current due to the holes will be given by charge, mobility, number of carriers, field plus the gradient for the holes. And finally, when we write the expression for the total current, I am going to add these two up. So, the total current is going to be the current due to the electrons plus the current due to the holes in a semiconductor system. So, this is what we have come to after discussing all sort of actions that the carriers in the semiconductors undergo. We have come up with a set of equations which we can now apply to a problem and see what will be the solution. So, let us see an example of how we will look at this problem of using this equation to solve a problem. Since we have not started discussing devices as yet, let us take up a problem which is only related to semiconductors and the processes that are happening. So, let me take a semiconductor and a semiconductor is such that it has let us say, let me define it as an n type semiconductor, which basically means its n naught is much greater than P naught, the equilibrium concentration, and since I am using the minority carrier diffusion minority carrier continuity equation, it means there is no concentration gradient for n and p here. So, I can use that equation. So, n naught is not a function of x. So, it is a uniformly doped semiconductor, and then I find a way to generate let us say I am going to find a way to generate carriers, and I am going to generate carriers in this material, which is by photo excitation, such that the electron generation is equal to hole generation, and I can then write it as just G of L, and I am doing it uniformly throughout the semiconductor. So, I am trying to remove the space variation in the generation. So, G L is generation rate, which is constant throughout. So, this is a constant throughout, and I want to see what will happen to the carrier concentration. So, at t is equal to 0, the carrier concentration is n naught and p naught, and the material is majority n type. So, n naught is much greater than p naught, and hence the minority carrier that we are worried about is delta p. That is what we will be solving for, and I want to find out that t is equal to 0, it is n naught and p naught, which basically means delta p is 0. So, there were no excess carriers in the material. At t is equal to 0, I find a way to generate carriers, let us say photo excitation, such that at every point I am generating carriers at a constant rate, and which is given by G L, and I want to find out how is delta p changing as a function of time. This is what I want to find out, and I am going to use the minority carrier continuity equation to do that. So, I will use the minority carrier continuity equation for excess carriers, and this is for p here, diffusion the excess carrier concentration for holes minus So, this is the equation that I need to solve. So, let us first try to see what will happen in steady state. So, at t is equal to 0, we know delta p is equal to 0, but what will happen at t is equal to infinity? So, first case is at t is equal to infinity. So, as I am shining light on the material, it is generating more and more carriers, delta p and delta n are increasing with time, and when you generate excess carrier, what will happen? Because of the recombination, because of this term, they will be recombining. So, eventually a time will come when the generation rate will be equal to the recombination rate, and at that point you are going to have a steady state carrier concentration in the material. So, if I look at that situation in a steady state, t is equal to infinity, in steady state basically I am saying this is going to be 0. So, there is no change with time in a steady state. What is happening to the first term here? Since I am generating excess carrier at the same rate throughout the material, which has been shown here, which means this term is also 0, which basically means I am left with concentration, excess carrier concentration, which means at t is equal to 0, the excess carrier concentration will be given by G L times tau of p. So, this gives me what would be the eventual carrier concentration in steady state in the material if I am generating carriers by some means throughout the material at a uniform rate. Now, if this is happening at steady state, what is happening in between? So, what is happening from t to t infinity? Obviously, we have gone from excess carrier being 0 to excess carrier being a steady state value. So, we need to look at what will happen in the what is the transient phase. So, if we look at the transient phase, then again we write the same equation and see how we will solve it for the initial and final condition. So, which means the excess carrier concentration, the second term is still, first term is still 0, and the second term is given by Now, this is a well known differential equation which has a solution which is given by change in the solution for this equation will be of the form delta p as a function of time will be given by g of L tau p plus a exponential minus t over tau p, and this if one solve for the initial condition at t is equal to 0, delta p is 0, delta p at 0 is 0, and at t is equal to infinity, and we need only one value here to solve, delta p at infinity is that we have seen earlier g of L tau of p. If we solve for this, which means delta p of t is changing, and this will give us an expression for 1 minus exponential minus t over tau p. And if we try to plot what is happening in this system as a function of time t, you can immediately see that if t is 0, what will happen? If t is 0, then 1 minus 1 is 0, there are no carriers. This is the condition here, that at t is equal to 0, there are no carriers, delta p is being plotted here, and as t becomes very large, this will increase as 1 minus of the exponential function. Eventually, it will go to the value of g L of tau p, and this with 1 minus of the exponential function, it is going to change. So, this is consistent with what physically what we see by solving the minority equation. In the similar manner, we will solve these continuity equation when we talk about devices and find a solution, and at this point we will leave you with the final equations that need to be solved for any particular device, which are the in the general form. These are the equations where you need to know what is the charge in your material, what is the field inside your device, what are the current densities, and when one solves all these equations, one has taken into account all the carrier actions that are taking place in a semi-conducting device. So, this is the starting of our discussion for the next module, module 4, where we will use these to look at what device characteristics look like, which basically means what is the current density as a function of voltage. The second example for using minority carrier diffusion equation, this is taken again, we assume a silicon semiconductor which is in thermal equilibrium at t is equal to 0. At t is equal to the thermal equilibrium, and then I shine light at a edge at time t is equal to 0, and I am generating a carrier concentration at time t is equal to 0. I have generated, let us say again this is a n type material, and I have generated excess carrier concentration at x is equal to 0 by shining light on it at t is equal to 0, and then I stop shining light. So, what will happen to this carrier as it at time t greater than 0? This is what the question is. So, the question is, if I take a semiconductor, I shine light on one end, and I have a region up to which I will create carriers because of that. Rest of the bulk of the material do not have any carriers, and I want to figure out whatever excess carriers I have generated at time t is equal to 0, how will they diffuse into this material. So, again it is a problem of minority carrier diffusion, and so if we write that the minority carrier equation for this is going to be, this is not going to be a steady state solution, because this concentration of the carriers here is going to change with time. So, we are looking for a transient solution. Plus, now since we had illuminated this at time t is equal to 0, and then after that we shut off the light, the photo generation for time t greater than 0 can be assumed to be 0. It is as if we created excess carriers, and after that there is no photo generation in rest of the material. This part is going to be 0. This part will not be 0 because as you can see there is already a gradient, there is much higher concentration of holes here compared to the rest of the material, and hence this gradient is going to exist, and this term will of course exist which is due to thermal cases, and this is a solution that I am looking for in solving this particular problem. So, when one solves this problem, one would see that it is basically being driven by the diffusion of the excess carriers into the semiconductors, and a solution for that can be obtained, which we have shown in one of the examples here. And then that can be applied to our solution to find the delta p n. If I plot the solution as a function of time in x, the concentration of x's whole carrier initially at time t is equal to 0, I have a step function at time t is equal to 0, and as the time progresses we will see this is going to diffuse, and the solution is going to be represented by a moving front which is going diffusing as well as moving in this direction because of electric field that is generated. So, this is what happens when we have a minority carrier diffusion equation and we try to apply to certain situations. Once again this is an example which is used quite often, because when we are trying to calculate the diffusion constant of the n or diffusion constant of the holes, what is very important is the diffusion length for the n, which is given by square root of diffusion constant of the hole multiplied by the lifetime of the electrons, or for holes it will be given by the diffusion constant for the holes multiplied by the lifetime of the holes, and this is what will decide what will be the final distribution here. So, I have shown in summary examples, two examples where we use the equation of a state or continuity equation, a special case of it where we are applying it to the minority carrier diffusion in the devices, and two examples in which how we use it and what are the solutions that we get, and these solutions then later will be used in the next module to look at the devices.